Hi guys, in today's session we're going to be looking at global circulation, and this is a GCSE topic and you will know this from your GCSE work in the first unit, and we're going to be looking at the movement of the circulation cells. I'll be talking you through those processes, and we'll also be looking at one of the case studies, which is the Mali case study, which looks at why Mali has a wet and a dry season. So we're going to start off with what is happening at the equator. And we're going to start off with our Hadley cell. So we'll get stuck straight in. And what's happening here at the equator is that this overhead sun is heating up the land at the equator, and it's heating it up really, really intensely. And there's a couple of reasons for that, which also come up in some of your questions on your GCSE paper. The first reason is because of the curvature of the Earth, we have this area around the tropics and around the equator that are actually physically closer to the sun. So they will receive more solar insolation from the sun anyway. The second reason, if you remember, is that the atmosphere that the sun comes through here, because it's facing the sun, the amount of atmosphere that the sun has to come through is quite short or quite small compared to when we have the curvature of the Earth further north. Those sun's rays are coming through a lot thicker amount of atmosphere, so they have to spread out more, so the heat is more dispersed. So for those two reasons, the area around the equator has very, very intense heating. So let's see what's happening in our Hadley cell. The ground is heated by the sun, as I've just said, and that very, very hot land then becomes very, very warm, and that heats up the air directly above it. When the air heats directly above it, we know what happens when hot air gets warm is that it rises. So this hot air rises from the equator into the atmosphere, it cools, it condenses, and it forms clouds. And mostly what will happen then is that we'll have rainfall. So this area around the equator is a band of very, very heavy rainfall. Now all year round really, this area has a lot of heavy rainfall. And you know this because in year 9, I'm sure that most of you were looking at ecosystems. And the ecosystem that is associated with this area of intense rainfall is the tropical rainforest. And we know that tropical rainforest has very high biodiversity, and the two main reasons are it's very, very hot and it's very, very wet. So we know from previous studies that this is an area that has constant heavy rainfall and constant high temperatures. So that shouldn't be anything, that should be not new to us. So this area here, as we said here, this is also called the ITCZ. This in your textbooks, when it's talking about the ITCZ, all it means is the junction between the two Hadley cells north and south of the equator. And I'm just going to talk you through the ITCZ. ITCZ stands for Intertropical, so we're at the equator and we're between the tropics, hence intertropical. Convergence, two areas of air converge at the equator, and zone, it's an area. So the intertropical convergence zone is this low pressure area of heavy rainfall that's associated with the high intensity of heating of the overhead sun. So as that air rises off the ground, if we remember, that leaves low pressure on the ground. So that air's risen, it's cooled, it's condensed, it forms clouds and it's rained. So what happens to that air then? As the air rises, it cools. So as air cools, it's less able to keep hold of moisture. When air's very, very warm, it can hold lots and lots of moisture, so it doesn't really rain. But as the air rises and cools, the amount of moisture that it's able to keep hold of before it rains is lessened. So this is why we get heavy rainfall. When the air rises, as I just said, it cools, it wants to sink back down. Of course it does. It can't because there is air underneath it pushing upwards. So what does it do? It spreads out either side, north and south of the equator. So some of that cooler air goes north, some of it goes south. So what does cool air want to do? It wants to sink. So it sinks at about 30 degrees north and south of the equator. And this sinking corresponds with the areas of desert. In the northern hemisphere, over Africa, we have got the Sahara Desert. In the southern hemisphere, we've got the Kalahari Desert. So this air sinks, and as it sinks, it starts to warm up again as it reaches still quite warm temperatures within the tropics. But that sinking air causes the pressure on the ground to be high. If we remember, high pressure means the air is pushing down. So the high pressure is talking about the surface pressure, not the pressure up in the air. So don't get confused about that. So this air sinks. As it sinks, it wants to move out again. It's got to move somewhere. It can't stay where it is. So what it does is it finds the nearest area of low pressure, because it can then start rising again. So some of it moves southwards, back into our ITCZ, back to the equator, and this sets up our first circulation cell, which is the Hadley cell. And this Hadley cell is responsible for, like we said, for the ITCZ. So that's our first cell. Now, if you'll notice a little X here, this little X is Marley, and we'll come back to Marley in a little while. So this is our first cell. You can see that it's mirrored in the southern hemisphere, because the air, as it rises, it moves north and south and sinks both 30 degrees north and 30 degrees south. So it sets up high pressure areas north and south of the equator. And as I said before, the Sahara Desert, high pressure, hot but no rain. And the Kalahari Desert, which is around Namibia, just north of South Africa, hot but no rain. And you might be thinking, why can deserts have no rain? And this is why, because there's high pressure there. And high pressure means, if we remember, that air cannot rise, it isn't rising, it isn't cooling, condensing, forming clouds and raining. So that high pressure means that there are hot but dry conditions. So that is our Hadley cell. This is a convection current, which I just said before. So the ITCZ is this band of rain that we have associated in the middle of the Hadley zone. Right, so what does the air do then? Well, some of it, as we just said before, once it's dropped over the Sahara Desert, over 30 degrees north roughly, some of it moves north and some south. As it moves northwards, it's relatively warm air. As it moves northwards, we know this because we get lots and lots of this air from the Caribbean hitting the UK shore, and I'll do another video on that maybe at some other time. And as it goes northwards, it's still quite warm, and it meets colder air, which we'll talk about the polar cell in a second, but it meets colder air coming from the poles, and that forces that warm air to rise yet again, and the same things happens as happened here. So that warm air hits the cold air, rises, cools, condenses, forms clouds and rains. So this is our second belt or band of heavy rainfall, and our second area of low pressure. And if you remember, low pressure is always associated with rainfall, high pressure is always associated with dry conditions. So this is over the UK. I'm going to draw a little triangle here. Now unfortunately, we will be plagued by this low pressure nearly all year round, because we are maritime and we're at that little junction between the feral and the polar cell. So we're always destined to have a lot of rain in the UK. So that air rises, as I said, it cools, it condenses and forms clouds and rains. But again, it's cooler air now, so it wants to drop. But again, it can't drop back down because it's been pushed from behind, from other warm air. So what does it do? That spreads out as well. So some of that air comes southwards and drops down over the desert, and that starts our feral cell. So this is another circulation cell, and that's the feral cell, and that's the one that has an impact on the UK. Now, as we said before, some of it also moves northwards. It's still pretty cold, moves northwards, gets even colder and drops down again over the poles and causes high pressure. Now again, you'll remember this from ecosystems, because when we were up here looking at our ecosystems, we talked about tundra, and we called tundra a cold desert. And a desert just means that rainfall is kind of way, way below 500 millimetres, sometimes below 300 or 250 millimetres. So this area is an area of very high pressure. So high pressure means that the air is dropping or sinking, so no rain, no condensation, etc. And that air flows southwards, and as I said before, it hits the warm air that's coming from this area of high pressure, and that forces it to rise. So all three cells are just following some fundamental bits of physics, which is that the air is blowing from high pressure to low pressure, warm air is rising, and cold air is sinking. So as long as we remember those processes, those really fundamental processes, then we shouldn't get too confused with our trisecular model and what's happening with bands of rainfall, etc. around the Earth. So these areas stay, these cells stay as they are. So let's think of what's happening now. So like I said before, these cells are staying where they are, but they seem to be moving. And the reason they seem to be moving, if we know, you know that we have seasons. So we have a summer and a winter, we have autumn and spring as well. And it seems like these bands are moving northwards and southwards. But if we just remember that the it's not the air masses that are moving, it's the earth that's moving. But it seems like, because we can't feel that movement, it seems like these air masses are moving. So the earth, as you know, is tilted forwards in the summer. That's what brings us a little bit closer to the sun and a little bit closer to those hot air masses. And in the wintertime, the globe tilts backwards. That takes us further away from the sun, and it means that the sun's rays have more atmosphere to get through, so we're a lot colder. So just remember that it's not these bands moving, it's the earth moving into and out of these bands that causes the movement of the seasons, that causes our seasons. So with that in mind, we're just going to have a little look at our Marley case study, and I'm just going to run through some of the little processes with you that it's worth learning, because often these may be standalone questions in the exam, and we could get asked about what happens in summer and winter and what happens to land and sea. So I'm just going to run over those as well. So let's take Marley, because we can explain it with our case study in mind. So we've got Marley here, which is basically in northwest Africa, if we remember. It's just off the coast, and it's kind of between the equator and the tropics. So it's between the low pressure and the high pressure zone. So it really is influenced by the movement of the ITCZ, which is the band of rainfall. But remember, it's not the bands of rainfall moving, it's Marley that's moving, or the earth that's moving Marley. So let's just consider some of the processes first before we look at Marley. So in summertime, if you remember, land heats very, very quickly. It's very, very good at absorbing heat. So it gets very hot. And remember what that does: if the land gets hot, it will heat the air above it. And that hot air will rise, cool, condense and form clouds. So during summertime, when the earth is tilted forward and Marley is actually in the ITCZ, then we've got this area of intense ice insulation. So Marley's getting really, really hot. That land is getting really hot. So the land gets hot, the air heats up, that air rises, cools, condenses, forms clouds, and it rains. And that gives Marley its wet season. So Marley will have quite high rainfall at that time of year. So that will hopefully answer your exam style question about why Marley has seasons. And we can also remember, we may well be able to answer the question about the differences between land and sea and how they heat up and cool down. So at this time, the land's getting hot. What's happening over the sea is that the sea at this point, at the beginning of the summer, if you remember, the sea is much cooler, because the sea takes a lot longer to heat up. So it's only by the end of the summer that we have the sea surface temperatures being very high, because it's had all summer to heat up. But at the very start of the summer, the sea is much cooler. So if the sea is cool, then it won't heat the air up immediately above it. So that air won't rise. So that sets up an area of high pressure. Now, if I go back a little bit, Marley, with the hot air rising, that obviously sets up an area of low pressure. Now remember what I said right at the beginning, is that air always flows from high pressure to low pressure. So we have high pressure over the sea and low pressure over the land during summertime. So that is giving Marley its rainfall. Hopefully you're still with me. So what happens then is, in the winter time, the earth tilts backwards and Marley moves out of the ITCZ, or it seems like the ITCZ is moving away from Marley. So what's happening in winter? Well, now the ITCZ is much further south because the earth's tilted backwards. So that means that the land is a lot cooler. Okay, it's not getting that same intense insulation that it was getting during the summer, because it was tilted more towards the earth. So here it's colder, land is colder, the air above it is cooler, so there's not as much rising, cooling, condensing and rainfall. So Marley is having higher pressure, because we know high pressure is when the air's on the ground. What's happening over the sea is that the sea is now very, very, very warm, because it's moving into winter. It's had all summer to heat up. So that is causing, if the oceans are hot, then that heats the air up above the oceans. That means that that warm air rises, cools, condenses and forms low pressure. So again, we've got the same things happening as air's moving from high to low pressure. So this gives Marley its dry season. Okay, hopefully we're okay with that. So that covers a couple of things. It covers summer and winter and land and sea, and hopefully also it should explain why Marley has got a dry season and a wet season. Now, just to finish, I've written a couple of asterisk points here that it's worth remembering. And the first one is that this air movement, these 3 cells in the northern hemisphere and 3 cells in the southern, they serve to redistribute heat. Okay, now we know that two things redistribute heat around the planet. One is ocean currents. That's their job, remember, it's to redistribute heat from the equator to the poles. And the other way that heat is redistributed is that those oceans will heat the air above them. So that warm air will also start moving north and south. And that's what's happening here. These three cells are redistributing heat around the globe. And that means that we don't get masses and masses of intense heating at the equator, so it's unbearable and unlivable, unhospitable. And also it moves air and rainfall further north, and it moves heat further north and further south. So that's the first job, to move heat from the equator to the poles. And secondly, I went over this before, but just to remind you, the ITCZ seems to move, doesn't it? It seems to be moving north and south, but remember, it's the Earth that's moving into the ITCZ and back out again. And therefore, that's how we're getting seasons around the world in different places. But it seems to us, because we don't feel that movement, we don't feel the spin of the Earth, and we don't feel that tilting, it seems like the ITCZ, the zone of high rainfall, is moving up and down during summer in the Northern Hemisphere and winter in the Southern Hemisphere. So I think that's everything covered. The main things are to remember what the ITCZ is and how it works, to remember your Mali case study, and to remember the differences between land and sea and how they heat and cool. So that this diagram, hopefully on global circulation, it should cover many questions, hopefully some 2 marks, some 4 marks, and some longer questions with our case study in the GCSE exam. So hopefully that's been useful.